Before I talk about the coronavirus model, I would like to talk about a slightly simpler model, the Measles Model. This is actually the model I based the coronavirus predictions off of with a few modifications. Here, society is broken into 4 compartments. People belonging to the susceptible group have not yet contacted the disease. Once people get infected, they can move to the pre-infectious group. The letter E instead of P is traditionally used to denote this group. At this stage, the infected person might not have symptoms and does not infect other people. After some time passes, the infected person himself becomes infectious. Anyone that contacts this person will also get infected. And after some more time, he recovers and gains immunity, so he cannot become infected again. The time that passes before an infectious person recovers depends on each person, but we can use the average rate and apply to everyone. A lowercase r is used for this rate. Similarly, we can use the letter F to denote the rate at which an infected person becomes infectious. Notice that F and R depend only on the disease. There is also a rate at which a susceptible person becomes infected. This rate depends on the infectiousness of the disease as well as how many people are infectious at that time. Since the number of infectious people, IT, changes over time, this rate, which we'll call the force of infection and label with lambda, also changes over time. Lambda is expressed as beta times IT, where beta is the per capita rate at which 2 people come into effective contact. We'll talk more about this in later videos. Based on the model, we can write out 4 differential equations that show how each compartment changes over time. Notice that the susceptible group is always shrinking at a rate of lambda. This will shrink over time as there are fewer people to infect. The shrink in S is precisely added into the E group. And with the rate of F, people in the E group can move to the infectious I group. Similarly, we can make sense of how the infectious and the recovered groups change over time. There are some important assumptions that we need to remember when dealing with this model. First, it's deterministic. This means that eventually, everyone gets the disease and goes through recovery. Second, it's short-term. The population is constant and there are no births or deaths. In particular, there are no deaths caused by the disease. Third, it assumes random mixing. In other words, we're assuming that people behave like air particles and can be expected to contact people far away. These are strong assumptions that allow us to have an easier job modeling the disease, but at the same time it can lead to unrealistic predictions.